Maxwell's equations go in and they show us that the electric field and the magnetic fields are related. And as we start observing things, we start to see that they're going to interact together, and ultimately we end up with the electromagnetic spectrum. You can think of the electromagnetic spectrum as light packets. I do in some of my videos, I go through a history and we actually start back with the idea of a charge. And the charge goes all the way back to the Greeks, at least in Western civilization, we go all the way back to the Greeks and we look at how those things are happening. And then we look at the various observations that people had. What's interesting is that people don't necessarily think that about Isaac Newton being actually one of the folks that deals with light, but he was one of the individuals that actually started looking at light and trying to explain light. Hooke's law also was looking at light. And then you also have Galileo and everybody else. So if you think about Hooke, Hooke was looking at light going smaller because he's more from the biology side where we get it. And he has these lovely drawings of the flea, and we do get that. And then we have the other items where other people were looking at the stars. So you had things where we were looking at light and magnification, and then that we had looked at light and bringing it in from out in space. So we're going to talk about that transition from electricity to optics, because what happens is, as we're dealing with science and going through it, and physics, remember, was a natural philosophy, we start looking at things that we're going through there. So one of the things that we know about light is that light or electromagnetic waves sometimes are going to behave like a particle. So Newton looked at particles like reflection and refraction. So if I take a ball and I bounce it off of a wall, we have the law of reflection, where the angle that the ball makes from the normal is going to be the way that it bounces off. And we played with that in billiards. We played with that in momentum. We played with that in a lot of different areas. It also behaves in the bending of light as we deal with refraction. So as I change, if I take a ball and I throw it into the water, the medium that I'm in is going to cause a bend or a change. So waves or particles can explain reflection and refraction pretty well. And when we do geometric optics, where we're dealing with mirrors and looking at the rays with mirrors, you can kind of follow it along just by using those rays and bouncing them around just like you would balls or different billiard balls. But then we had Huygens, and we actually talked about Huygens and wave fronts back when we were dealing with sound, which is why I like to start with simple harmonic motion and mechanical waves in physics 2. Sometimes you get those mechanical waves in physics 1, depending on where you are. But we do get those pieces there. And Huygens comes out and he shows that any part of the wave front can be the source of a new wave. So we do get that idea that light can behave like a wave. And we'll see that in just a little bit when we look at the Young's double slit experiment, where that Huygens principle that any point on my ray front or my wave front becomes the source of another wave. We'll actually see that. Now, Maxwell was the one that really tied those four equations together, made the correction, and we now see that the magnetic field and the electric field comes together. And it's not too far of a stretch to take us to quantum after that. So that's really what happens after Maxwell. We start dealing with, okay, now we have this really strange behavior, this wave behavior, and we start looking at how waves are going to interact and the wave packets. And part of a lot of quantum mechanics comes from the fact that we're starting to try to explain this duality of light. And then article light can act as a particle. And he explained the photoelectric effect, and then we use Planck's ideas of energy, and we can all tie it back together. But this is really an area where, as we've kind of laughed over time, that, and in fact, at the meeting I was talking about states of matter. If I'm in chemistry, we tell you there are 3 states of matter. If I'm in physics, we tell you there's 4 states of matter until you get to upper division physics, and then we can tell you there's 9 to 13 states of matter, maybe 15 states of matter. And it's all on how you're looking at the different things, trying to explain what you're observing. Newtonian mechanics gets us a long way. Looking at light as a wave gets us a long way. Looking at light as a particle gets us a long way. But when you try to explain the Hall effect or the photoelectric effect or some of these other things, then it becomes a little tougher. And we have to dig a little deeper, and we have to take more things into consideration. So many of us have seen the Young's double slit experiment. We've either seen it in a wave pool, or we've seen it in a variety of things. We see that interference, additiveness of waves coming together, either being a mechanical wave like in water or a light wave. We're going to get a pattern that comes in there, and you can actually see that. And in order to explain that, you have to explain light as a wave. So the Young double slit experiment said we use Huygens principle, we bring in a wave front, we now can take that wave front, which can be another source. There we get a slit, and we get a nice interference pattern. And we can use that to our advantage. And in fact, all my graduate research used this to an advantage, because what we looked at is the forces that cause these gaps between nanometer-sized particles, and we looked at the changes in the diffraction pattern that we got, and we could actually interact. And if we knew the mass of the particle, we knew the charge on the particle, we could actually look at the van der Waals forces associated with nanoparticles, and we could actually measure those and pull those out just by looking at the diffraction patterns. These diffraction patterns, the Young double slit experiment actually expands out to allow us to do diffraction patterns that allows us to do X-ray crystallography. We can look at liquids. We can discern a number of different things, looking at how the waves are going to go through a slit or are blocked by a particle. And those diffraction patterns give us information about crystal formation. So we actually use that to our advantage. So some experiments, to explain what we're seeing, we have to look at light as a particle. Some experiments we have to look at to explain it as a wave. Now, what's really interesting is that the debate in science at the time was such that we end up with the biggest disrespect that occurs, because they were arguing and saying, well, light has to be a wave or light has to be a particle. At the time, there was no idea that it could be both. And that's where we end up getting this idea of Poisson spot. So the national academies, this was one of those big things, the national academies in Germany, National Academy of Science in Germany was arguing about energy. The national academies in England was looking at Faraday's, and then the French Academy was arguing, is light a particle or a wave? And you end up with this idea in 1818 where Fresnel comes in and says, hey, we can look at the diffraction, and he sponsored it. And Poisson comes out and says, no, that's not going to work. If it does, you would take a round object, and if you put light around it, it would form a spot, and the spot's not there. Well, Fresnel goes and does the experiment, and the spot is there, and therefore they were actually able to show that light will bend around an object, and so it's going to have more of that wave behavior, and they named it Poisson spot because Poisson actually argued that it wouldn't be there. And so it was quite an interesting debate going back and forth. So we call our light particles photons. And a photon, you can think of it as a wave packet, you can think of it as something else, but each photon is going to have a particular energy, and that's going to be based on the frequency that we saw. We use Planck's constant, and that photon is going to be able to encompass both natures. And you could see that by looking at that electric field and magnetic field diagram that we talked about last week. So you do have that. So reflection and refraction, the process of reflection and refraction can occur, and the process of refraction is related to changing from one medium to another. So we see refraction all the time. So if I stick a straw into a clear liquid, looks like the straw breaks or bends. You can play with laser light and you can see the laser light having things bend. And you can look at it from that perspective. You also, if you're sitting down at the bottom of a pool and you look up, if you look straight up, you're going to see things kind of cockeyed going from one way or the other, because as the light moves from one medium to the next, you're going to get that bend either outward or inward, depending on what that is. Now, reflection, the light's just bouncing. We bounce lights in mirrors. That's how periscopes work. That's how you can set up instrumentation to bounce light mirrors so you can see around a corner. All of that works out, and we're going to use that idea of reflection to help us explain the images that are formed by mirrors. And both processes can occur at the same time. And I actually have a picture of that. So lights, we're going to use geometric optics. We call it ray optics. We're going to make an assumption. And now with laser pointers, it's a lot easier to see, because you can think of our ray as a laser pointer. You can think of it as the beam that's coming from the laser, and we can move it. So light's going to travel in a straight line until it encounters another medium, or it's going to be bounced off of a surface. So we do that. So we're going to use that ray approximation. So the ray is an imaginary line, and you can think of it as that laser line. So a laser pointer gives you a good idea. Now, what that ray is just one tiny piece of our wavefront. Just like looking at that water wavefront that we had, we're going to look at that and be able to expand it. So the rays are going to correspond to the direction of the wave. And we're going to follow one little line here. We're going to follow this one little line, and we're going to use that to represent our light. So we call that the incident ray, the ray that's coming in, and it's going to travel. And then we're going to look at how it hits. So we talk about specular reflection. So when my ray comes in, it hits my surface and it bounces off. So if this is a mirrored surface, you're going to see that bounce. And if this is a perfectly smooth surface, you're going to get nice, even reflections of it bouncing off. And you can see that here with a laser light doing the exact same thing. Now, when we talk about the angle related to the normal, remember this is going to be my normal to the surface, and we're going to look at the angle. Oops, this is my normal to the surface, and we're going to be looking at that angle and how it goes there. So if I look at this, the angle of incidence is going to equal the angle of reflection. And now you've got diffuse reflection, like what you see. This would be more like why we put the little crystals in the paint on the edge of the road, so that the line or the yellow line shows up really, really well. And it's going to give us something like that, because the light's going to bounce depending upon the actual surface that we have. So we can look at this. So here's our diagram with the normal actually drawn in. And this is the law of reflection. Don't make it more complicated than it is, because it is very straightforward. We do have that. There's my angle of incidence. Here's my angle of reflection, and they're going to be equal. They're going to be equal, and we can look at that. So if I have a problem where I have my periscope, you're going to come in, you're going to draw it, and you come out and you draw it. Now, the thing about geometric optics is that you can do it graphically, as well as mathematically, and you can actually have it work. And it works very, very well. So we just have that nice angle of refraction. So now we're going to get into refraction. So refraction is that bending, okay? It's that bending of the light. So here's where we say you can have both processes happening at the same time. So if I have a piece of glass, I can have my incident ray come in, and part of my incident ray will be reflected, and part of my incident ray will be refracted. And you can have it bend that way. And so you look at it, so you can have these things come in. So I have my incident ray coming in, I have my reflected ray, I have my refracted ray, I have a reflected ray, and then I have a refracted ray. And this is called smoked glass so that you can actually see it. So doing some manipulation, what we do show is that these angles are going to be some sort of a constant. And we're going to actually use that constant to really help us out. We're going to call it an index of refraction. And we're going to actually have that. So the material, so we actually have it if this index of refraction is greater than the material. So in air, it's really, really close to 1. Vacuum, it is 1. But in air, it's really, really close to 1. In glass, it's going to be some number bigger than that. It's going to bend towards the normal. So if I'm going from a lower index of refraction to a higher one, we're going to get a bend towards the normal. It'll go the other way if we go from glass to air, we're going to get a bend away. And that index of refraction is the speed of light in a vacuum divided by the speed of light in the medium. And so we're going to get a slight change. And you can actually tell the difference between certain clear liquids in organic chemistry by using the index of refraction. Toluene is going to be different than xylene, which will be different than benzene. And you can actually tell the difference between the materials based on their indexes of refraction, which is really, was really slick. So for a vacuum, n is equal to 1. For any other medium, n is going to be greater than 1. It's a unitless ratio, and the value increases as the wave decreases. Now, the thing that we have to worry about and have to explain, and we end up having to deal with regard to our material, is that as light travels from one medium to the other, the frequency does not change. Both the wave speed and the wavelength do. Otherwise, you would just be building up light waves at the surface. So you have a difference there. So light is going to behave a little differently, but the frequency doesn't change. I mean, you don't see a change in the frequency. So you'll end up having that part work. So you can play with that. Remember, our speed equation is our velocity is equal to the frequency times the wavelength, and we can play with those ratios. But here is a table of some of the indexes of refraction, and we will use Snell's law. Snell's law is pretty straightforward, fairly easy to use, but you've got to know what your indexes of refraction are. And Snell's law is saying that the index of refraction from one material and the angle of incidence is going to be equal to the index of refraction of the other material and the sine of the angle of refraction. And we utilize that to deal with that bending that we see so that you do have that. So dispersion is that spreading out of our light or wavelength. And so the dependence on our wavelength is considered dispersion. And we'll see that dispersion in a variety of places. Different colored light may have different indexes of refraction, depending on what kind of glass that we're using. And you'll get a little bit of difference in bending. And how our prism works out. If I have white light, this is Y, because each color is going to refract a little differently. depending upon its energy and all of that good stuff. That's why we're going to be able to split out the colors of the rainbow. And that's why we get violet will deviate the most and red will deviate the least. And we're able to get that spreading out of our white light, because white light has each of these colors in it. And we are able to utilize that idea of dispersion in order to have my prism actually divided out. So we use spectrophotometers a lot to do that. That's how we're going to be able to play with different materials and look at the energies. You know, a hydrogen atom is going to have different energies of light coming off of it than others, and we're going to be able to see distinctive lines and characteristic spectra. So you will get that. We see that in gas. We use it in chemistry. That talks to us about energy levels. And it's that energy part that we pay attention to in chemistry. And that's going to give us those materials. Remember that we can use that spectrophotometry to be able to tell us what the composition of the sun is, or what the composition of a particular gas is based on those energy levels that we have. Hydrogen is going to look different than helium. And it turns out that we discovered helium on the sun using spectrophotometry long before we were able to find helium here on planet Earth. So we use that spectral analysis to identify molecules. We use it to identify distant stars. We use it to identify minerals. And we can either use absorption spectra or reflective spectra. Either way, we can actually utilize that in order to help us. So the rainbow, how's the rainbow done? Well, the water droplet's going to act like a prism. We're going to get that refraction, and it's going to bend out, and you're going to be able to get the light to come through. You get that dispersion. You get the lovely rainbow that we see. And double rainbows, those are just second order, third order effects. Sometimes you can actually see a third one. It's not very often, but you can actually see a third one on characteristics. So Huygens, we just talked about his principle. We've talked about it a couple of times. And he was using that geometric construction, which is what we're going to actually use at all points on a wavefront, can be taken as a wavelet, and we can utilize that to move forward. So here's another way of looking at it. We can utilize each one of those little pieces, and we can use that for geometric objects. There we go. So you can actually play with the geometry. He actually showed it mathematically that Snell's laws works and our angles of refraction work. So you can actually work through that and play with those different geometries. So a couple of other concepts that we need to talk about. If you've ever sat on the bottom of the pool and looked up, all of a sudden you'll see a mirrored surface. You won't be able to see out, and that's related to total internal reflection. At some point, we hit a critical angle that all of the light will no longer be able to escape the surface, and it will be totally reflected. This is important because we use this for fiber optics. This is how we allow fiber optics to work, and it explains what we actually see. And you can easily detect the critical angle as a ratio of our indexes of refraction. So you have those. And again, fiber optics was exactly where that comes from. All right, so we've made our transition between electromagnetics to optics. What we're going to do tomorrow is we're going to look at mirrors. We'll look at flat mirrors and spherical mirrors. Then Monday, we'll look at lenses. And then we're done. I mean, it works pretty well. Now, you do have all the videos and all the PowerPoints that are available. If you're starting ahead and wanting to look ahead, my big caution is to look at the charts associated with your sign conventions, because that's really what's going to help you with your problems that are out there. So I'll open it up for questions.
For the refraction assignment, whenever we're using
Uh-huh.
the simulator, what exactly do you want us to put in our discussion? about that? Just filling in the questions that are in the PDF
Yeah,
sheet? Or...
just to answer the questions. You can, and I would prefer it to be in paragraph form rather than the answer to question one or the other. Just